All right, y'all, let's go ahead and rock and roll. How's everybody doing? I saw one thumb up, two thumbs up. Any more thumbs up, or are we all just like three? Okay. Anybody ever heard that line like, I wish I had three hands so I could give that three thumbs down? All right. Okay, so today we're going to talk about really our last big class of biomolecules. Right. So just as a really quick recap, we started off by introducing amino acids really from the perspective of acid-base chemistry, right? Thinking about the functional properties of amino acids, especially focusing on their acid-base properties. We then introduced nucleic acids and talked about how nucleic acids can polymerize into DNA and RNA polymers and discussed the structure of those to some degree. And then on Monday, we talked about lipids, right? And how fatty acids are long carbon chains with a carboxylic acid functional group on one end. And we talked about how we can classify those as saturated or unsaturated. We talked about how we can easily name them and some themes that recur in biologically relevant fatty acids. And then kind of moved into thinking about how fatty acids can condense with glycerol to make triacylglycerides, fat molecules, right? Like that goes in our adipose tissue, or phospholipids. And then briefly talked about some of the functions and structures and functionality of lipid bilayers. Okay, so today we're moving on to carbohydrates. Okay, and really carbohydrates I think are this in many ways the easiest class of biomolecules because once you see the patterns, it tends to be fairly straightforward. However, the patterns sometimes are not as obvious as in other cases. Okay, so what I'm going to talk through today is really trying to point out some really important recurring themes in carbohydrates. And then really I want to give you a lot of time today to practice because drawing these and being able to convert between the linear form and the cyclical form of carbohydrates, that's where it takes practice. And then understanding how we can make carbohydrate polymers. Like that just kind of takes practice to draw. So my goal today is to give you plenty of time to do that. Okay, so first things first, at its very origin, carbohydrates are simply hydrated carbons, right? It is in a carbohydrate, for every carbon, there is a water molecule. So the empirical formula will always be CH2O, right? So if we look here, for every one carbon, there is one water molecule. This formula has to be true if a molecule is a carbohydrate, okay? So if you just count atoms, it's really easy to quickly figure out if something is a carbohydrate or not. It has to fall into this overall formula. Let's close this door. I don't want to listen to a vacuum. Okay, so that's the overall idea here, right? That's what a carbohydrate is. And they will always fall into one of two categories, an aldose or a ketose. Okay, an aldose has an aldehyde functional group. It'll have one aldehyde functional group. If you find more than one carbonyl in something that you think is a carbohydrate, think again, it can't be a carbohydrate. If you have more than one carbonyl, there simply will not be the CH2O empirical formula. Okay? So it can either be an aldose or a ketose. The aldose contains an aldehyde, the ketose contains a ketone. Okay? And for our purposes, for most biologically relevant carbohydrates, the ketone falls on carbon number 2. Okay, so one carbon away from one of the ends of the chain. Okay, so a carbohydrate has to have an empirical formula of CH2O. It can fall into the category of aldose or ketose, meaning it contains an aldehyde or a ketone. And then the other way that we name them, that we can classify them, is based on the carbon chain length. Okay, so if it has 3 carbons, it's a triose. If it has 4 carbons, guess what it is? A tetrose, right? A pentose, a hexose. So we name these things as aldotrioses, aldotetrose, aldopentose, or ketotriose. Okay, fairly straightforward. So essentially every carbohydrate you ever see will fall into these categories as of being an aldo, triose, aldopentose, aldoketose, etc. Aldohexose. Okay, and You can easily draw these things out using like any Lewis structure that you want, but at the end of the day, it's most useful to draw them as Fisher projections. You may remember Fisher projections from organic. The idea is pretty simple. It's we line up the carbons in a straight line, and then stereochemistry is implied by the direction that things are pointing, right? And quite frankly, I don't care if you remember your stereochemistry. There is one carbon that we actually care about. The rest of them we don't care at all about, okay? But Fisher projections are really, really useful because you can very quickly see the stereochemistry around each chiral center, okay? And as we'll talk about shortly, the only chiral center that actually matters is the one that's the farthest away from our carbonyl. Okay, this is the one that classifies the sugar as either D or L, which we'll talk about here in a second. Okay, so looking at our Fisher projections or our linear projections of these two hexoses, one is a ketose, one is an aldose, right? Very easy to see here that our ketose, or sorry, our aldose has an aldehyde and our ketose has a ketone. Okay, one of these is glucose, one of these is fructose. Fructose is an aldohexose. So this one is glucose. Fructose is the ketohexose. So this one's this one's fructose. The only difference between glucose and fructose, two really common, really important sugars in biology, is the positioning of the carbonyl. One's an aldose, one is a ketose. That's the only difference. Otherwise, the stereochemistry around each carbon is identical. Okay, so they're simple isomers. Okay, I mentioned that we really only care about one chiral center, and that's the one that's the furthest away from the carbonyl. Okay, it'll never be the very end of the chain because the very end of the chain is not a chiral carbon. There's always two hydrogens and one alcohol. Okay, so this very last carbon is never chiral. So it's always the one that's second to last. Okay, so if you have 7 carbons, it's going to be carbon 6 that's the last chiral one. If you have 4, it'll be carbon 3. Okay, if the alcohol group points to the left in your Fisher projection, this is L, an L sugar. If it points to the right, it's D. And I think this is easy to remember, right? L points left. The hydroxyl group is higher priority, and L sugar, the hydroxyl points left. So if the hydroxyl groups are pointing left on the last chiral carbon, they're L sugars. If it's pointing right, they're D sugars. In biology, we almost exclusively see the D isomers. Okay, it's D sugars that are most important. Okay, and that narrows down drawing these things by 50%, right? Because we immediately exclude 50% of our isomers because 50% of the isomers are L sugars, and we don't care about L sugars. We care about D sugars. Okay, so if you're asked to draw sugars, and you will be, if you're asked to draw them, you immediately know the orientation of one of the alcohol groups. On the last chiral carbon, the furthest away from your carbonyl, it has to point to the right because they're always going to be D sugars. Okay, and then beyond that, there are a very large number of possibilities for isomers, right? Every chiral carbon can have 2 isomers. The hydroxyl group can point left, the hydroxyl group can point right on each of them. So you can go through and predict exactly how many isomers you can have. We won't do it, but you can. What I want to point out here are the ones that have some biological relevance. Okay, and at the end of the day, I'm really only going to ask you to remember how to draw 2 of them. Okay, because everything else is an isomer of those. Okay, so ribose is of course, is an incredibly common biological sugar. So I need you to remember the pattern for ribose. Ribose is easy. Look, everything points right. Okay, so ribose is a 5-carbon aldose, and all of the hydroxyl groups point right. You can't forget that. Ribose, they point right. Okay, arabinose and xylose are also important biological sugars that only differ from ribose by the orientation of a single hydroxyl group. Okay, so arabinose, note that carbon 2, the hydroxyl group points left, and on xylose, on carbon 3, the hydroxyl group points left. These are called epimers. Okay, so if I tell you that Xylose is the C3 epimer of ribose. Since you know the structure of ribose, everything points right, and xylose is the C3 epimer, what this means is it looks exactly like ribose, except the hydroxyl group on carbon 3 points the opposite direction. And since you know on ribose it points to the right, that means on xylose it must point to the left. Okay? If you remember ribose, I will tell you the orientation of the other ones, right? Anything that deviates, I will tell you that they are epimers at that position. Straightforward? Okay. Same thing goes with our aldohexoses. Here, of course, glucose is incredibly important. Remember the pattern of group glucose. Right, left, right, right. Okay, remember right, left, right, right. If you remember that, you can always draw glucose. Right, left, right, right. And then the other important biological sugars, biological aldohexoses, are all epimers of glucose, meaning they differ by a single carbon's orientation. Mannose, we see here, is going to be the C2 epimer of glucose. Glucose points right on C2, mannose points left. So if I asked you to draw mannose, I would tell you it's the C2 epimer of glucose. And then you know to flip the orientation of C2. Galactose is the C4 epimer of glucose. The most relevant biological sugars are epimers of ribose or glucose, at least the aldoses. Okay? Ribose. Aldopentose, 5 carbons, aldehyde, right, right, right. Glucose. Aldohexose, 6 carbons, aldehyde on carbon number 1, right, left, right, right. If you remember that, everything is easy from then on. Ketoses, there's actually fewer variations because there are fewer chiral carbons. Okay, right? So carbon number 1 is not chiral. The last carbon is not chiral. The carbonyl carbon is not chiral. So we've actually limited the number of possible isomers for our ketoses. But nonetheless, there's some important biological ketoses. Okay, ribulose is the ketose isomer of ribose. If you can draw ribose, move the carbonyl from C1 to C2, right? The carbonyl is on C2, and then the rest of them point right, right. Ribulose is the ketose equivalent of ribose. If you can draw ribose, simply move the carbonyl from C1 to C2, everything else stays the same, and you're done. Same thing goes with fructose. Fructose is the ketose isomer of glucose. Move the carbonyl from C1 to C2, everything else is the same, and you're done. Okay, remember glucose, the pattern is right, left, right, right. So on carbon 2, there's no right or left, it's a ketone, but then it goes left, right, right. It follows the same pattern. Okay, if you draw them side by side, as we did on the second slide of the lecture, the only difference was the positioning of that carbonyl. Any questions about that? Okay. So then at this point, go ahead and take some time to work through the first several questions in the activity. This is a fairly long activity, so I'm going to try to give you plenty of time to do it in class today. The first 9 kind of go through this idea of drawing out the Fisher projections and identifying whether molecules are carbohydrates or not.